In the previous lecture, we discussed transport properties of quantum dots. Those are quasi-zero dimensional structures, but under the framework of classical electrostatics. So in this lecture, we will discuss the transport properties of these quantum dots when the quantum mechanical properties of electrons, quantum nature of electrons are dominating. So we'll discuss the single particle level spacing and its effect on the transport, the forked Darwin states, artificial atoms and shell filling, and eventually thermal effect or temperature on the transport and thermometry. As we just mentioned, we considered only classical dots so far, or the classical electrostatics and its effect on the transport properties. The context was the dots were metallic or large quantum dots where the single particle level spacing is negligible and the density of states inside the dot is continuous. So the total energy that the quantum dot got is just its electrostatic energy, that is CgVg minus Ne all squared divided by 2c sigma, where this corresponds to the charge on the gate and this corresponds to the number of electrons. C sigma is the total capacitance. So the energy required to add an electron onto the dot is the energy difference between the states n plus 1 and n, and from a direct substitution that you can realize that this is nothing but the charging energy. That means the same amount of energy required to add charges or electrons successively. And the Coulomb blockade oscillations that we discuss is basically the oscillations in the current, and every peak represent two charge states degenerate, and number of peaks represent the number of electrons that you have added or removed from the dot. And the spacing of these peaks are equal because you are applying the same energy or same shift in the energy to align different levels with the source and the drain. So you have regularly spaced peaks, and every peak is separated by the same charge or same gate voltage, delta V, and delta Vg, and addition of every electron requires same amount of energy, Ec. Now let us consider that these levels are not really continuous, those are discrete. And that is the case when you have small semiconductor quantum dots. So the addition energy is not just the difference in the electrostatic energy, but you also have these single particle states delta n coming in the picture. So in addition to the electrostatic barrier that you need to cross to add an electron onto the dot, you also need to basically satisfy its internal energy levels. Okay, that means these peaks may not be equally spaced because you also have the spin degeneracy present. Okay, so when you put the first electron, okay, this peak corresponds to first electron. Next electron is just the charging energy because it's going to the same orbital or same shell, you can consider, okay, same level. Now the next electron will take the charging energy and also the level spacing. It need to go to the next level here. and the next electron will occupy the same level because it is going to say anti-parallel to the existing electron, because those are spin degenerate states. Okay, but the next one will again take EC plus delta En. So you are going to see a kind of doubly periodic oscillation. So there will be two periodicity. Okay, because you will have this addition of the level spacing coming in every other transition or every other addition of electron into the dot. That is the case when you have the level spacing equal. All the levels are equally separated. But that is not the case always, because the level spacing depends on the geometry of the confinement. Just from this one-dimensional examples from basic quantum mechanics, we know that level spacing is equal for a parabolic quantum bell, one-dimensional quantum bell. But that is not true for most of the other cases. For example, this is for a square well. Well, the level spacing increases, and for a hydrogen atom kind of potential well, it's going to decrease. Okay, so the level spacing will be seen in the position of the Coulomb blockade oscillation. Or just from the periodicity of the oscillation, you can understand what kind of potential you got. You don't need to worry too much about any other spectroscopy. Just a current voltage measurement is going to tell you what is the nature of confinement you have. Okay, so rather than resorting to some other spectroscopic techniques of this quantum dot, directly a DC measurement or a low frequency AC measurement, which is kind of DC itself, okay, because it's a very low frequency measurement, you can understand the kind of confinement, the pattern, how the quantum dot is going to get filled. Okay, now let's consider the quantum dot, which is the shape of a circular disk. And as we discussed, most of these quantum dots that we discuss and technologically important are gated quantum dots. That means you form the quantum dot by confining the electrons by applying gate voltages. Those are electrostatically confined quantum dots, and those quantum wells we have seen in case of the quantum point contact, where the barriers are mostly parabolic. They're best represented as parabolic confinement. So when you have a circular disk, what you have is you have a two-dimensional parabolic confinement, or the well is going to look something like this, or the dot is kind of shape of a disk or a pancake, and the quantum well is going to look parabolic in all the directions in the XY plane. And this is a well-known potential and well-known problem, and the wave functions for this, for the Hamiltonian, when you have a two-dimensional parabolic confinement, are called Fock-Darwin states. And these images represent the first few states, or the probability density of first few states. And here the energy levels are given by this equation here, where n and m are the quantum numbers. And this shows the degeneracy and the filling sequence for these different energy states. Okay. So what we are seeing here is, when you have a two-dimensional parabolic confinement, you have a filling sequence. The first level can take 2 electrons, second level can take 4 electrons, third can take 6 electrons, fourth can take 8 electrons. Okay, so these are like the shell's structure in a natural atom, okay, where you have 1s2, 2s2, 2p6, 3s2, and so on. So can consider this is like an s orbital, this is like a p orbital, and so on. Okay. So the first closed shell you can consider 2e because this completely closes this energy state, this energy level. Okay. This is one. And second one can take 4 electron. When you fill 4 in the second level, that state is also completely closed. Similarly, the next one can take 6 electron total. That means when you fill that, you will close that shell also. And similarly, next one, 8. Okay. Next one, 8 electrons. So the closed shell configuration for this quantum well, just like in a natural atom, but remember natural atom is a 3-dimensional, this is a 2-dimensional atom, okay, is 2e, that is when this is closed. The next one is 6e, because then 2e, this is closed and this is also closed. That means 2 plus 4, 6, okay, 2 plus 4, 6. And the third one will be, if you supply another 6 more electrons, that means 2 plus 4 plus 6, that will be 12. That is this case here. The next one will be 20. 2 plus 4 plus 6 plus 8, because the fourth shell can take 80 electrons. So that will be a total of 20 electrons. So these are the closed shell configuration for a circular disk quantum dot. So there is a very clear and close analogy between the natural atom and these quantum dots here. Natural atom has a shell filling sequence. When you go from the left side to the right side of the periodic table, you add 1 electron. When you reach there, the eightmost one is a completely closed shell configuration. And when you go to the next, you will start filling the next, okay, next orbital and so on. So you have next shell and so on, okay. So very similar to that, you also have a shell filling sequence in case of this artificial atoms. These quantum dots often referred to as artificial atoms because these are man-made structures but which mimics the shell filling sequence of a natural atom. Okay, so there is a lot of, as I was saying, there are lots of analogies between these two. As we have seen just now, the natural atom, you understand the shell filling sequence and this atomic structure by spectroscopy techniques using lasers. But here, you can understand shell filling sequence as we just looked in by currents and voltages, because you can run currents and voltages into these artificial atoms or quantum dots, because those are slightly larger. They provide you the provisions. There are provisions to apply voltage and measure the current, which is not possible with the natural atom. So here you can directly measure from a simple transport measurement the shell filling and the atomic structure. You can characterize the atomic structure. Okay. So there are a lot of analogies and there are a lot of advantages in this case. A lot of atomic physics experiments you can do just by using currents and voltages on an artificial atom or quantum dot. Okay. So what we just discussed is the closed shell configurations for this atom in the shape of a pancake or circular disk is 2 electron, 6 electron, 12 electron, 20 electron. Those are the shell filling or completely filled shell configurations. Okay. Now this is not just a mathematical construct. It has experimentally shown that the artificial atom actually follows this sequence. In a very famous landmark experiment, which is published in this article, this group has shown that the artificial atom also follows very clear shell-filling sequence, and they also have made a periodic table for the artificial atoms. So the quantum dot is made from a gallium arsenide, indium gallium arsenide, aluminum gallium arsenide heterostructure. The stacking sequence is given here. And this is like a vertical pillar kind of quantum dot, but the cross section of the quantum dot is like circular. Okay. And they have provisions to apply voltages along the vertical direction and run the current along the vertical direction. The biasing condition is shown here, and there are well resolved single particle states here. Okay, and these are extremely small quantum dots, just for your information. And this is a picture of the device. And the Coulomb blockade oscillations are shown here for the first 20 electrons, first 20 electrons, first 12 electrons. Okay. So remember from the previous slide, you have closed configuration for 2, 6, 12, and 20. That means once you fill 2, then the next filling you will need to change the shell. That shell can take 4. Okay, so you will have to apply the charging energy plus the additional energy, which is the level spacing, or the shell energy of that energy that you need to apply to go to the next shell. Okay, delta En. Okay, and that additional energy will be there whenever you jump to next shell. That means between 2 and 4, and 4 and 6, 6 and 8, so on. Okay, so, and that is what they have seen here. You can see that 1, 2, once you have 2 electrons, then the gap is more, because you have an extra delta En here. Okay, then next 4, 1, 2, 3, 4, then again the gap is small. The next 6, 2, 3, 4, 5, 6, again you can see a larger gap, and so on. Okay, and the same thing is reflected in the Coulomb diamond plot also here. As you can see, you have a lot of small diamonds. Small diamond means lower energy, lower addition energy. Okay, this is 0, 1, 2 is 1, 2. Okay, then you have 1 electron, second electron. So diamond, reading the energy from diamond is a little bit tricky. So the way you have to consider, so you have to work out here is 0 electron, 1 electron here. As soon as you enter this diamond, you have 1 electron. As soon as you enter this diamond, you have 2 electrons. But this is the energy, the width of that diamond is energy that you need to apply for the next electron. Okay, so you have 1 electron here, 2 electron here, third electron is here, but to reach third electron state, you have to go this far. Okay, to reach the third electron state, you have to go this far. So width of second diamond will be more. Okay. Similarly, the width of the 6th diamond will be more. The width of the 12th diamond will be more compared to the nearest ones. That tells you that the addition energy is being applied after 2nd, after 6th, and after the 12th. Okay. This is what you are seeing from here also. This is nothing but just a line cut or a cross section of this plot along the gate voltage axis. Okay, and here they have a calculated addition energy, that is after 2nd, then 6th, 12th, you can see that additional energy for all those things are more. Okay. And for this configuration, remember, the three-dimensional atom has 8 groups. Okay. But for this configuration, you have only, you have this, for this configuration, these are the kind of periodic table. This is a periodic table which represents how these shells are going to get filled. These are all for different electronic configuration. In a natural atom, when you go from the left side to right side, you walk through various elements. But here, you're not doing that. You just change the gate voltage and you have various number of electrons inside. But that's exactly what's happening in natural atom also, because the constituents are proton, neutron, and protons, neutrons, and electrons, right? All you are doing is you are changing the number of protons, neutrons, and electrons. Here, this periodic table has just one quantum dot. It represents one quantum dot with various charge configurations. Because when you vary the gate voltage, you are going to fill successive shells and you will move through the periodic table from left to right. That's what you are doing. 1 and 2, then 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and 8 at last. Okay? That's what it is. The point I am trying to say here is this doesn't represent 8 different quantum dots. It does not represent that. It represents same quantum dot, but 8 different gate voltage configurations. Okay, that's what it is. Or if you have n number, n atomic number, then there are n different configurations for the gate voltage. There you are walking through various elements by changing the number of protons, neutrons, and electrons. Here, you are walking through the gate voltage space, where the shell filling configuration is different for different gate voltage. So this is a periodic table for the artificial atoms. Okay. And as you can see, the closed cell configurations are 2, then you have 6, 2, then 12, then 20. Those are the closed cell configuration as we just discussed. Okay. Now, this is the case for an atom, a gated 2-dimensional circular shaped quantum dot or artificial atom. But as I told, the confinements are different for different kinds of quantum dots. For example, here you have a quantum dot which is made of carbon nanotube. Okay, the sketch of the device is here. And interestingly, the carbon nanotube you have, because of confinement, you have an offset in the subband. Okay, a small offset is the delta, small delta written here between 2 subbands. So capital delta is the single particle states, but there is an offset between the 2 k and k prime states, and each of them can actually take 2 electrons, so there will be total 4 electrons. Okay, what that means is the filling sequence or the Coulomb-Bloch oscillation need to represent this 4 different states in energy spacing, and that's what you are actually seeing here. The filling sequence is we have 1, 2, 3, then the 4th, there's a large one. Again, 1, 2, 3, 4th large one. The way to understand this is you have the subband offset, small delta, and you have the single particle level spacing, capital delta. In addition to that, you also have a electrostatic term, a Coulombic term, du, and you also have an exchange term, J. And the filling sequence is demonstrated here, how you fill it. So you start from the one electron which is already there, then the next electron is going to fill the same state. The second electron will go to the next level, that is basically charging energy plus delta, that's offset. The story of metallic carbon nanotube based quantum dots are slightly different, but very interesting. In the previous slide, we saw the shell filling sequence for a disc-shaped, circular disc-shaped quantum dot. What we have here is a quantum dot released by a very short metallic carbon nanotube. And the energy wave vector or EK diagram is shown here. The confinement is going to give you discrete K states, and there are two subbands. The energy level spacing is delta, and the subband offset is small delta here. Okay. And you also have two more parameters to consider. One is the exchange J, and the other term is the excess Coulombic energy du. Details are provided in this paper. But what I want to highlight or invite your attention to is the fourfold filling sequence. If you take a Coulomb blockade oscillation, you can see that there are 4 peaks together, then there is a large gap, then again 4 peak, large gap, like that. There is a filling sequence of 4, then there is a large energy gap. Filling sequence of 4, then there is a large energy gap. And that's what you're seeing when you have the Coulomb diamond plot also. You have 1, 2, 3, then we have 4 electrons, and the 5th one takes more energy to fill. Okay, the diamonds are larger. The charging energy plus the energy spacing between the levels, that is more for the 5th. So the way it is understood is the following way. So you have the first electron that will take charging energy plus there is an excess Coulombic energy plus the exchange. The second electron will have charging energy plus the offset, band offset, minus the Coulombic energy. Then the third electron is going to go in the same orbital, the same level. So you will have again same energy as the first one. The fourth one is not going to jump into the next level itself. So you have the charging energy plus delta, the level spacing, but then these two terms are not there. Okay, that is how you need to look at this sequence, filling sequence. So you have 1, 2nd, 3rd, 4th, then you have the 5th one that is going to take 5th one filling more. Okay, 1, 2, 3, 4, 5th one filling more, like that. So this is again another proof that you can just take the current versus voltage measurement or transconductors measurement, and you can get the information on the shell filling or the structure of the artificial atom. In this case, it is for a carbon nanotube based quantum dot. Okay. Now, this is another example where you can do the spectroscopy of this artificial atom. In this case, what we are seeing is the effect of magnetic field induced spin splitting or the Zeeman split states that you can directly probe from the transport. So you have more or less circular shaped quantum dot, which are realized by electrostatic gating, and you have in-plane field, parallel field, which will split the spin degenerate states in the absence of field into each of them into two, separated by the Zeeman energy EC, which is G mu B into B, where G is the lambda G factor, and mu is the Bohr magnetron, and B is the field, parallel B field. So in the absence of the field, you have these spin degenerate levels, single level. Two spin states have same energy. So when they cross the Fermi level, when you vary the gate voltage, that's going to give you a peak, which is the Coulomb blockade oscillation. When you vary the gate voltage, you are actually lifting or lowering these levels in the parabola. And every time when one of these level crosses, you get one peak. This is the case when you don't have any field. The field is zero. The moment you have a field, what happens? Each of this level will split into two. So, but this is again a single electron transport regime. That means you can only put one electron at a time. Okay. So what that means is when the first level comes in the window, you get a peak. But when that level disappears, then closely the second level is going to follow. So these are pretty close compared to these single particle levels. The Zeeman splitting is small compared to the single particle level. That is assumption here. Okay. Then you have the second level will come in the picture. Then you get again a peak corresponding to that. So what are you seeing here is each of these peak will split into two, and the separation is the Zeeman energy. Okay. So from this, you can see that when you take a Coulomb diamond plot, this is the gate voltage axis and this is the bias axis. This is the VG. This is the V drain source voltage. Okay. So the line cut along the gate voltage, that is the Coulomb blockade oscillation. The line cut along the gate voltage basically is going to give you basically two peaks. Okay. Each of this line here correspond to one of this peak. So you have the initial Coulomb diamond. This is one part of the Coulomb diamond, one edge of the Coulomb diamond. Then you are going to have parallel lines which represents the splitting at the edges of the diamond. And which diamond these lines running into, then the spins, the Zeeman split states represent that lines correspond to that charge configuration. The splitting correspond to that charge configuration. Okay. Now, in this case, this splitting here correspond to the n is equal to 1 configuration. Okay. Anyway, those are details which which falls beyond the scope of this lecture. But in a nutshell, the splitting delta in the gate voltage axis, it is delta Vg is basically a function, is linearly related to the Zeeman energy EZ. Okay. Now, they can calculate what is that Zeeman energy corresponding to using the geometry of the diamond, this size of the diamond and the voltage scale. You can calculate what is the G factor, because G factor, the splitting and G factor are proportional. So the G factor is a constant, so splitting and the Zeeman energy are proportional. From using this relation, you can calculate G factor. Okay, and G factor, you can also, probe and understand the variation G factor because of the confinement, or variation G factor because of other effects such as spin orbit coupling and any other effects. Okay, so you can probe all this just by using transport measurements on the quantum dot. Okay, this is another example. Now, this monodots are really small or nanoscale objects where they behave like artificial atoms. So what we are seeing here is a painting or stained glass, a 13th century art form with the Gothic cathedral windows. Okay, all these colors are actually painted by colloidals of gold nanoparticle, but with various size. So as we saw in the one of the previous slides, where the property or the shell configuration or the filling sequence, the filling configuration changes as you change the gate voltage. But when you change the size of these nanoparticles, you are actually going to modify its filling sequence also. Okay. In that way, from the same material but with different size, you can get different properties, different electronic properties. So all these colors are generated by gold nanoparticles of various sizes. Okay. Here is another example where the gold colored nanoparticle displays the spectrum of colors as a function of their size, starting from 2 nanometer through 150 nanometer. Okay. The same technique is being used in 13th century Gothic cathedral window paintings. Another data where the melting point is going to change as a function of the particle size. When you have small nanoparticle, nano gold, the melting point is so low, and when it reaches large size, it is going to approach the bulk melting point. So every physical property is going to depend on the electronic structure, and in case of quantum dots, the electronic structure is its size, or how many electrons are present, how many excess electrons are present, or what is the shell filling. Okay. And that is why these quantum dots are also called artificial atom, because just like natural atoms, you can vary its property just by varying this electronic shell filling configuration. Now, let us discuss one last topic today in this class. That is the thermal broadening of the Coulomb blockade oscillation. So what is the effect of temperature on this Coulomb blockade oscillation? So the classical dot, where the temperature energy is more than the single particle level or the level broadening, but the charging energy is much larger than that, then only you will see the Coulomb blockade peak or oscillation or the charging effect. Okay. In that regime, the conductance peak is given by this formula. Okay. Here, with the full width at half maximum for 0.35 kPt. Okay. So what we are seeing is the full width at half maximum, or the peak width or the peak shape, depends mostly on the temperature here. So just by varying the temperature, and you take the Coulomb blockade oscillation and fit using the formula, you can calculate the temperature accurately at very accurately for these devices. Okay, and this is a valuable tool because the temperature of the equipment that you are using to measure these quantum dots, generally these measurements are done at low temperature. So the temperature of electrons are very different from the temperature of the equipment, or even the temperature of the crystal, because the electron-photon coupling is very weak at low temperature, where these measurements are done. These measurements are done at less than 1 Kelvin, cryogenic temperature regime, quite often tens of millikelvin. That temperature, almost no electron-photon coupling, so the crystal won't help to cool the electrons. So you have to cool the electrons separately with additional filtering and other mechanisms, other techniques. So it is very, very important to get an accurate measurement of the temperature of electrons to know where you are standing, what is energy scale. Because the temperature energy of this electron should be much, much lower than any other energy scales in the problem. Then only you can observe those effects. Okay. So it's very important to know the temperature, and this is the technique that generally used to obtain the temperature, because you just take the Coulomb-Blocher oscillation of the corner dot, then you fit it with temperature, you vary the temperature, and rest of the parameters are same, but only the temperature is varying. So you can do a global fit, and you can find out what is the temperature for this device. And in the other regime where we have quantum mechanical properties are actually dominant, then the peak shape is given by this formula. But here, the small difference, I mean, it's a crucial difference, is the peak height is also a function of the temperature. Because the transmission through the quantum dot is also a function of temperature. In this case, transmission is not a function of temperature, but the peak height is always same. In the quantum mechanical case, the peak height is also going to vary. Okay. So in the zero temperature limit, it's always a resonant transition. So the width it's a delta function. So it's a width is almost negligible. But as you increase temperature, the Coulomb-Blocher oscillation peaks will get broader, but at the same time it also will get shorter. Okay. So this is the regime where you have the charging energy and the delta, the single particle level spacings are greater than the temperature. The broadening is actually less than the temperature. You don't have a lot of broadening, but the single particle level is much, much larger. Okay. In this case, the peak height is also a function of temperature. Whereas in the classical case, the amplitude of the peak remains same, but the peak is going to get broadened. Okay. So in both of those regimes, you can use this formula to determine what is the temperature of the device, what is the electron temperature of the device. And of course, mostly in the experiments, one deals with, or one uses classical dots or larger dots, because it's much easier to fit, because there is only, the temperature appears only at one place, it's only in the exponent, so it's only in this function here, in the argument of this function here, whereas in this case the temperature appears in two different places, and the fitting process is slightly more complicated. So always the temperature is estimated using large quantum dots and fitting the Coulomb-Blocher oscillation as a function of temperature. Okay.